because I don't want, like, I've actually got cash, and I don't, I need to get rid of it. So have as many drinks as you can possibly imagine. I wrote some notes. They were coherent and disorganized, and then I never even looked at them. So I don't know even where to start. Let's not worry about my notes. Let's just try and think about where we were up to. So what I tried to teach you so far today, I've made the following observation, right? Let's let K be a number field. Okay? And let's let S be a finite set of finite places. Okay? And now let's consider gal K S over K. Right? That's an infinite global Galois group. And we've got names for various conjugacy classes. Right? Frob P, for P not in S. Okay, these are conjugacy. They're not really elements, they're conjugacy classes. So let's just kind of cheat and let's just choose an element in each conjugacy class. Okay? So here's what I was trying to say in the last hour, right? If this gal Ks over K happened to be a free abelian group, a free group. It's definitely not abelian. But if it just happened to be a free group, kind of freely generated by these Frob P's, then we would not even be here. We could all just go home, because it would be easy to write down representations of this, because we could just send Frobenius to anywhere we like, okay? And then that would be great, right? Then we could define rho from gal Ks over K to gln of QL bar, because this is a random free group, and we know the generators by just choosing random matrices. MP in gln of QL bar for all P not in S. Right, and then send Frob P to MP. And then we've finished, right? There's all the global Gal representations. Okay, so if that was a free abelian group generated by this, and then the global Langlands conjectures would say, right, the global Langlands conjectures would say, take any old pi, take any old irreducible representation, pi, of gln of Diadels of K. Okay, take any random, okay, and we get rho pi, right? And the way we get rho pi is some tensor product of pi v there, and pi p is maybe unramified there, and so pi p goes to rho p, and rho p is unramified, and rho p of Frob p could just be m, could just be mp, and I'll just define, I'll define rho of Frob p to be mp for all p, and then just extend it, and there's our thing, right? That would be what the world would look like if this was a free group, freely generated by Frobenius, who would have complete freedom in defining Gal representations, who would just send Frobenii to anything. Okay, and that would translate on this side to, we could just write down any representation of this group, and then once we've got some local situation sorted out, we just get some global situation for free. Okay, so that's not true, right? This if, that's not true. That's wrong. Okay, so what's the truth? The truth is that this is some profinite group that's certainly generated by these Frob P's, but there's infinitely many really, really complicated relations that nobody in the world understands. Okay, so that's the truth of the matter. All the Frob P's are related in some vastly complex way. which no human understands, right? For example, I can just let k be the rational numbers, and I can let s be the set of primes 2, 3, and 5. And then for each prime p at least 7, I've got conjugacy classes from p in this. And I could ask, is it true, can I choose an element in the frob 7 conjugacy class and an element in the frob 13 conjugacy class that multiply together to give an element in the frob 23 conjugacy class? It's kind of like, that's a pretty random question, and it's the kind of, it's somehow difficult to work out the answers to those questions. So they're related in some, there are relations, right? So Chebotarev says that they somehow generate. Chebotarev says that the frob P are dense. You see, in fact, Chebotarev gives us a proof that there are relations, right? So Chebotarev says, I've got all these primes P not in S. I get frob P, conjugacy classes for all those primes P. And Chebotarev says that they're a dense subset of that Galois group. And I just take one random prime P and remove it. Chebotarev still says that resulting things are dense. So the one frob P that you removed, it's in the topological closure of all those other things. So that one frob P you've removed is about the limit of other frob Ps. What are those other frob Ps? Right? And what the limit, is it equal to one of these other frob Ps? It's just like nobody really knows, nobody really can figure out what those relations are, because we don't have a good tool for understanding this very abstract thing, because we don't really even know what KS is somehow. Okay? So those are related in some really complicated way, and to write down a compatible system of L-adic Galois representations of this Galois group is really, really hard, right? We know two ways of doing it. One of them is et al. Cohomology of algebraic varieties, which is code for Tate curve, for Tate module and cyclotomic character. And the other way is limits of these things. That's all we know, right? So an automorphic representation cannot be a random collection of representations of GLN of the Adels of K tensored together, because if it were, then that would somehow correspond to this thing just being free. So we could define a global representation by randomly defining it locally. So I've suggested in the last lecture, I've attempted to motivate the fact that, based on our observations for GL1, based on our successes. Ooh, no, don't put it there, because then it falls off. Put it there. Based on successes for GL1, we will restrict to representations pi of GLN of the Adels of K, which show up in A0 of G, right? Or A of G. I mean A0 of GLN over K, right? Which is going to be the space of nice functions from GLN of the Adels of K over GLN of K. Oh, I better not write it like that. It's really a left GLN of K to C. Okay, and we restrict to these nice functions, and then maybe that will be, maybe everything will be great. So what's a nice function, okay? What's a nice function? Well, let's try and make some guesses, right? What do we know, right? I mean, for n equals 1, what was nice, right? Grierson characters were nice. Right? We want Grierson characters to be in there, in fact. Because if a Grierson character is in there, then GLN of the Adels of K will act on that space. If I've got chi, some Grierson character, right, then chi is really literally a function from GL1 of the Adels of K to C, right? I normally write to C star, but it is a function, just considered as an abstract function. It does go from GL1 of the Adels of K to C, right? It actually lands in C star, but I just want to think of it as a function to C, and then it's trivial on GL1 of k, which is really good. So it looks like it might be in this A0. And now, how does GL1 of the Adels of k act on chi? This is gonna work really well, isn't it? So let's say a Grierson character is nice. Then my Grierson character will give me some function here. Now let's just define G star phi of gamma. G star chi of gamma is by definition chi of gamma G. And that's by definition chi of G times chi of gamma, because it's a group homomorphism, right? You see? And therefore, G star chi of gamma equals chi of G times chi, right? By functional extensionality, that's called. I didn't know that last week. Functional extensionality means that two functions are equal if and only if they're equal on all arguments, which is a triviality unless you do constructive mathematics, in which case it's something you need to worry about a lot, apparently. So let's not do constructive mathematics. So if a Grierson character is nice, and it will be nice, then it's going to live in there, and lo and behold, that it will span a one-dimensional vector space, right? C of chi, that's a one-dimensional vector space, right? And GL1 of the Adels of k acts on that space via chi. So Grierson characters are going to be nice. So Grierson characters, I guess by continuity, says that Grierson characters are locally constant at the finite places, right? If I look at chi of kind of OK hat star, that's some finite thing. They're locally constant at the finite places, and they're sort of smooth at the infinite places, right? Because they're like x goes to x to the power s. Okay. And in fact, they're more than smooth, right? They're more than smooth, right? They're more than smooth. If I write down some random function on the reals, right? So I'm trying to guess what these nice functions are. All I know is that Grierson characters look kind of nice. So let's look at what Grierson characters are really doing, and let's see if I can just think of some abstract. You see, here's the problem. I defined a Grierson character to be a group homomorphism. This is the point. This is the problem. For GL1, life was easy. I defined a Grierson character to be a group homomorphism, and everything was fine. We don't have a group now, right? This is a group. This is a non-normal subgroup if n is bigger than 1. So we can't talk about group homomorphisms from that weird set theoretic quotient. So this is an issue, right? At infinity, the Grierson characters, we looked at functions x goes to x to the s, okay? And they're smooth, but they're better than smooth. They're group homomorphisms. And we can't say that here. I want to map from GLN of the reals modulo GLN of z to the complexes. Doesn't make sense. It's more than smooth. Okay, it's really nice. I'll tell you one thing it's not growing too fast, right? It's not growing too fast. Right? I could look at x goes to e to the e to the e to the x to the s instead, right? That would be growing kind of quickly, right? So it's not growing too fast. It's infinitely differentiable, but it's more than that. It's more than that. How am I going to capture the fact that it's a group homomorphism without using the word group homomorphism? Let's differentiate it. Maybe calculus will work. X goes to x to the power s. I'm not very good at calculus. I've been avoiding analysis all the time. So let me just do this very carefully. X of s log x. There. Let's define f of x. F of x equals x to the power s, which is x of egg log s. So now let me define f dash. Now I'm just kind of f dashed of x. I'm just wondering if maybe it satisfies a differential equation. But I actually am incapable of differentiating x to the s on the fly, so I have to do it. So it's x, derivative of x of something is itself. And now I take the derivative of what's in the bracket. The derivative of s log x, if I differentiate with respect to log x, I can just differentiate this with respect to x. It's s over x, right? And so that's x to the power s times s over x. Is that right? I'm not very good at calculus. I think that looks okay. Okay, and therefore x times f dashed of x, I'm just tidying up, equals s times x to the s. That's s times f of x. Oh, great. There, so it's a differential. So it satisfies the differential equation. Great. Have I got it wrong? I want to write x times f dashed of x. I can't. This is all kind of stupid in the corner. X times f dashed of x equals s times x to the s. And that equals s times f of x. Is that right? Great. So it satisfies some differential equation that, I mean, I don't know. Is that some natural differential equation coming from the theory? How do we generalize? I mean, great. So Grierson characters, they're smooth, they're not growing too fast, I'm clutching at straws, they satisfy a differential equation. Differential equations. This is why I've been putting off the whole thing. We need to talk about differential equations. Because nice is going to have differential equations in, right? Because what I'm trying to do is I'm thinking, I know two examples of automorphic representations. And one of them is Grierson characters, and one of them is modular forms. And they just live in different worlds currently. And I want those worlds to slowly converge. And a modular form is holomorphic. And being holomorphic is satisfying a differential equation. And this x goes to x to the s, that's not anything to do with holomorphic, but it's satisfying some other differential equation. So I need some machinery that's going to spit out differential equations. Okay. So what does nice? So nice will mean, well, obviously GLN of k invariant, right? And it's going to mean smooth, locally constant at the finite places, smooth at the infinite places, differential equation, unboundedness. That must be the right answer. Let's talk about differential equations. So, interlude on differential equations. So this puts me in an interesting position because this is almost certainly a topic that I know by far less than almost everyone in the room. And I'm supposed to be teaching it you. So we have differential equations. So here's the idea. G is going to be a Lie group. Okay, e.g. GLN of the reals, or GLN of the complexes, or GLN of k infinity. These are good examples to keep in mind, because they're the only examples we care about. G is going to be a Lie group, so a real manifold with some kind of group structure which is nicely behaved. And there's something called the Lie algebra. Lie algebra of G. So that's called that, right? Curly G is the Lie algebra of G. So when I was doing my Lie group class, this much I was kind of happy with. I sort of understood tangent spaces of manifolds. So I sort of understood the Lie algebra of G. And now there's this weird thing. G is something to do with differential operators. On G. And I'm not too happy with this statement. But I'm pretty sure that's how it works. There's some exponential map, right? And it goes from G to G. Okay? And like let's do GLN of R because it's the only case we really care about. Okay? So if G is GLN of R, then this Lie algebra is supposed to be, I think people write kind of curly GLN of R, but it's just n by n matrices. And there's an exponential map. This is not C, sorry, this is G. There's an exponential map that goes from the Lie algebra is supposed to be the tangent space of the Lie group at the identity. And there's an exponential map, right? It's going to go m goes to x of m, which literally is 1 plus m squared over 2 factorial plus dot, dot, dot. I mean, why is that going to be invertible? Because like x of minus m is an inverse. There you go. So there's my random exponential map from the Lie group to the Lie algebra. And now there's some kind of, I am actually going to have to look at my notes now. Because there's some way of thinking about this as differential equations, isn't there? Here we go. If I've got x in G, then I'll give you a differential operator. I'll give you a differential operator on the C infinity functions from G to the complexes. That space there, right? I just want to look at all functions on G. I'm humiliated. You just know far more about it than me. Sorry. There's a differential operator, and if my notes are right, and I can't even guarantee that, it will send F. So the idea is that x star F, so x is in my Lie algebra, and I'm thinking of it as a differential operator, and I'm applying it to my function f. So that's going to be a new C infinity function from G to the complexes. So it makes sense to try and evaluate my new function at G. And my understanding of this is that the way this works is this is going to be, I'm going to do one of those leave a gap things that lecturers sometimes do. I've left a gap. It's f of G multiplied by exp of t times x. This is, maybe a cross is not the best of notation. This is just product in the group. So if t is 0, exp of 0 is 1. And if t is a little small thing, then exp of a small thing is nearly 1. So as t tends to 0, this tends to g. Okay? And so the idea is I'm differentiating g in the direction of x, right? And the way I'm moving in the direction of x is I'm looking at t times x. So there's my function of t. I'm going to take the derivative of that guy. And that's now still a function of t, right? And so I'm going to evaluate it at t equals 0. And that's now another function of g. So that's how differential. I'm sorry to kind of go through all this. This is probably trivial undergraduate stuff for some of you, but it's just stuff that I'm not very good at, and so I have to go through it at the pace I can manage. So there's a differential operator. And these are terrifying things, and they don't even commute with each other. like, I never really got the hang of, like, d by dx and d by dy definitely commute with each other. But we had things like kind of x times d by dx, and that doesn't commute. X times d by dx doesn't even commute with d by dx, right? So random differential operators don't maybe commute with each other. So if I have kind of x and y in G, x and y in the Lie algebra, then I don't think you would expect kind of x star y, what would you do, x star y star f. I don't think that's going to equal, won't equal y star x star f. And I think maybe there's some way of measuring this, right? Isn't that somehow isn't that how you somehow define x comma y? Maybe the difference of those things is some other differential operator that somehow, maybe there's some clever way. I don't really want to talk about calculus. I don't know the first thing about calculus. So there's these things called differential operators. Let's do an example. Let's do GL1, because I reckon I might get through GL1. Let's do an example. Let's do G is GL1 of the reals. That's R star. And then the Lie algebra G will be the reals. And now let's say I've got a function on the reals then. Let's say I've got f from G to C. So f from R star to C. And now G, the Lie algebra of R star is R, and the exponential map is just the normal exponential map. And I need to choose an x. And I don't think there's any point in choosing a random x, because they're all scalar multiples of each other. And so why don't I just choose x equals 1? OK? Because that's the easiest number I know in this context. If I choose x equals 0, then this will be 0, yeah? And x of 0 will be 1, and this will be f of g as a function of t, but it doesn't depend on t. And you differentiate it, you get 0. So 0 is going to kill everything. So let's let x be 1. Like, does the entire room know what the answer is? That's nice to know. I don't quite know what the answer is myself, or that's not true, because I worked it out this morning. But when that's no guarantee that when I work it out now, we'll get the same answer, unfortunately. But let me work it out in front of you, and if I do something stupid, you can yell. So I've got a function from G to C. I've got a function from R star to C. OK, so let's work out x star f. Right, I'm doing calculus. I'm doing calculus to this function R star via some definition that I read in a book on Lie groups. But this should surely turn into something that I understand. X star f of g, for g, a non-zero real number, equals d by dt of f of g multiplied by x is 1. Did I say that?
Yes.
Oh, yeah, great. X is 1. So this is just literally e to the power t. And now, there wasn't a bracket here, and there's a bracket, and there's another bracket, and this is t is 0. So that is how the Lie algebra of GL1 acts on functions on the Lie group of GL1. Let's see if I can make some sense of this. F of g times e to the t. Oh, crumbs. I've got to differentiate this with respect to t. I use the chain rule. Right, great. So I'm going to be able to do this. This is something at t equals 0. So this is some f of g times e to the t. So is f of something, so the derivative with respect to something is just f dashed of g times e to the t. And now I've got g times e to the t, and I need to differentiate that. And I remember, this looks fancy, but g is just a non-zero. Everything is a non-zero real number, right? And so this is a product. G is constant. So this is a constant times e to the t, and the derivative of that with respect to t is the same, yeah? It's the constant times e to the t. Have I got that right? I hope you're watching carefully, because I'm not very good at this. So this equals, now I evaluate at t is 0, so I get f dashed of g, e to the 0 is 1, times g. Right? I reckon that's what we get. So who knew, right? What I'm suggesting is, when you look at functions on GL1 of the reals, there's some kind of canonical differential operator associated with that story coming from the Lie algebra, and that canonical differential operator is not just the derivative, right? So the upshot is kind of x star f, whatever, x star f of x is just x times f dashed of x. There's no point calling it g. It's a positive real number. It's a non-negative x in r star. Okay? So there is our differential equation. We had curses. You see, if I knew this stuff, we did an example. So I'm going to have to ask you. Let's do an example. Let's do f of x equals x to the power s. I don't want to. I've already differentiated this once today. I'm not doing it again. Then x times f dashed of x is, can someone just tell me? Is it, I'm going to write that. Is that, people are nodding. Right, great. So I'm going to say x star f equals s times f, right? That's what's happened, right? Our example, we had this function that was shown up for Grierson characters, and we've applied this differential operator that's come from some kind of canonical theory of differential operators, and we found that x to the s, something that we were pretty convinced was a good idea, has turned out to be an eigenfunction for that differential operator. So that's kind of nice, because I want this to work for modular forms as well. And for modular forms, if maybe the differential operators are things like the Cauchy-Riemann equations, then somehow modular forms will work, they'll somehow, maybe if the differential operator is the Laplacian, right, d2 by dx squared plus d2 by dy squared, any harmonic form is killed by that. So if the differential operators turn out to be the Laplacian somehow, then modular forms will be eigenvalues for that differential operator. So there you go. Well, if you do GL2, then things spiral really quickly out of control. So we're buoyed by our success. So maybe I should say, what's going on here is this G in the Lie group, in the Lie algebra. If this has got some x, right? X is in the Lie algebra of G. X gives us a differential operator on these functions. From G to C. But it's not a random differential operator. It's somehow, I think it's left invariant. Is it a left? I think X is maybe left invariant. Is it a vector field? I never know what vector fields are. I think X must be a left invariant differential operator. Where's my definition? I had a definition that worked in general. Or is it gone? Oh, you can still see it. It's somehow, it looked like this. I had some X, and the idea is I feed in something on the right. It's G times some weird thing that depends on X. That was the story. It might be under here, I suppose. I think I rubbed it off. So the idea is this differential operator, it takes your function and your G, and it starts goofing around on the right. And so it's relatively well behaved if you start changing G by something on the left. So X is going to be a left invariant differential. I think I've just proved that somehow. I'm saying if I replace G by H times G, then all that calculation will just be exactly the same. All the G's will be H times G's. And then, yeah, not that bit there. That's just the very end bit. Like the actual definition. I'm just suggesting. Look at the definition of the differential operator. It doesn't really change much if I multiply G on the left by something. So these are left invariant differential operators, but they're not right invariant. But you see, that's why this has happened, right? Maybe I should say the reason that this differential operator became x d by dx. That's that's somehow invariant under the group action. I think that's somehow the point. If I decide to scale, then x could somehow become lambda x, and then I'll get lambda x d by d lambda x, and the lambdas somehow cancel. in some. You see, this random differential operator is actually somehow behaving well with respect to the group structure. Right, let's do GL2. So we have this vague idea that what's worked for us is eigenvalues of differential operators. Okay, then great. The Lie algebra of G is 2 by 2 matrices over the reals. And this kind of contains things of the form E, F, and H, and Z, right? These are just four. This is like 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, minus 1, and 1, 0, 0, 1. There, I've just written down, this is somehow some letters that have seemed to have, somebody wrote them down once and they stuck. So they're called E, F, H, and Z. And each one of these will give us a differential operator, right? Give a differential operator. Sorry? Where, what?
I want to ask something about the previous.
Go ahead.
So, I didn't understand the last remark. Are you scaling there?
Why are you asking me? Yeah, go on.
Are you scaling the operator F?
I'm pretty sure I learned it from a book that I'm pretty sure it's possible to make sense of the assertion that this is invariant under the group action. So let's say I've got F from G to C, okay? And now why don't I define a new F, kind of F tilde? So why don't I fix little g in G, right? And why don't I define F tilde from G to C by F tilde of X is F of GX, okay? So I'm scaling like that. And now there's hopefully some commutative diagram I can draw, right? I can do F, and then I can do X star F, but then I could do F tilde, and then I could do X star F tilde, or I could do X star F tilde. And I reckon they're the same, okay? Because I reckon that to prove, when you unravel what that says, what that will say is, look at that theorem there. If you change G to kind of H times G, then everything will go through, but all the G's will be H times G's, and then you could just change it back to G at the end. I mean, somehow, what I'm arguing is that changing G to H times G is so innocuous that you can do it at any point in the argument. And that's putting the tilde on here. Right? I should maybe put an H here. Whereas somehow changing G to G times H is kind of more complicated because G times H times e to the t is not really the same as G times e to the t times H, you see. So somehow changing G to G times H will have a much more disastrous effect on the calculations. So I think that observation must prove this. So these are left invariant differential operators. So back to GL2. You're happy? I'm going back to GL2. I've got 4 differential operators on functions from GL2 of the reals to the complexes. I once worked out a formula for these functions, and they were awful. They're absolutely awful, right? And I wrote something, and it's on the course website, okay? And I really did explicitly, I had some explicit functions on GL2 of R, and I took these matrices and exponentiated them, times them by t, exponentiated them, and then took derivatives. And even though I'm clearly slightly confused by the fact that differential d by dx and d by dy commute, right? But general differential operators, for some reason, don't commute with each other, right? This is a non-abelian group. So these are left invariant but not right invariant. And I think that you start multiplying them together, you get all kinds of craziness, right? So all of these, right? So what's going on here, right? Why don't I just let, I don't know, why don't I just let V be all the C infinity functions F from GL2 of R to the complexes? Okay, there's a perfectly good vector space, and now these differential operators, E, F, H, and Z, are all maps from V to V, right? And they don't commute. They're just they don't commute, they're awful, right? These maps do not commute. Okay, for example, if you do E times F and then you do F times E, this is like H or 2H or something. You know, there's some story. If you know about representation theory of SL2I, you'll know it better than me. So it's not really sensible to ask for a simultaneous eigenfunction, right? Therefore, it is a bad idea to ask for a simultaneous eigenfunction. Right? If a bunch of operators commute, then that's great, because they can probably all be diagonalized simultaneously or something. There might be a whole basis of simultaneous eigenfunctions. But if they don't commute, then somehow asking that something's an eigenvalue for all of them is just asking much too much. Because in particular, you'll be focusing on a subspace where they did all commute. And in fact that they don't commute is somehow exactly what makes, you know, the point is this has got some Lie bracket on, and the bracket is non-trivial. So we've got to make some kind of sense of this. I want the answer to be, I don't know what I want the answer to be. I want to find some kind of structure. This is a problem. They don't commute. I'm going to fix it. I'm going to fix it. So let me talk about universal enveloping algebras. Here's the fix. This is the worst thing, right? Having simultaneous eigenfunctions sounds like a really good idea, but these do not commute, okay? So I'm going to find, so here's the plan. Let's find a bunch of differential operators that commute. Because E, F, H, and Z certainly do not, right? And now I'm going to do a crazy thing, okay? So this G is a Lie algebra, right? Let's start with a Lie algebra, G. I guess G is GL2R. These Lie groups are real manifolds. So I'm going to start with the Lie algebra G over the reals. Okay, so that's some vector space. I mean, in our case, it's going to be a finite dimensional vector space, G over the reals, plus some bracket, right? There's some definition from G cross G to G. Okay, some bilinear bracket, and the idea is, you know, whatever. It's just something, plus some axioms. There's something called a Lie algebra. There's some axioms. It doesn't really matter what the axioms are. But I'll tell you something. The example that people always talk about is that G can be n by n matrices. And the way you define the bracket, you do this, A times B minus B times A. Okay? And when you think about it, for two random matrices, A and B, they don't commute. So A times B minus B times A will be some other random matrix, and that's what the bracket looks like. Okay? So this is quite nice, actually. So what I'm saying is, so this turns out to satisfy the axioms. There's some Jacobi triple thing that I'm never going to write down. But there's some axiom, and if you do A times B minus B times A, when you substitute it in, everything cancels. Okay? So another example. If I've got if R is actually an algebra over the reals, so i.e. R is a ring, right? I've got a plus and a times, not necessarily commutative. I mean, an example would be n by n matrices. let's say I've got an algebra over R, so that means I have a product. Right? The difference between a Lie algebra and an algebra is on a Lie algebra, all you have is the bracket, but on on an associative algebra, if you like, on an associative algebra, you actually have a product. And when you have a product, you can form a bracket, right? You've got an associative algebra. That gives you a Lie algebra. Okay? Because you've got A, you've got R, and its product. Then you get the same Lie algebra R, and you define A comma B equals A times B minus B times A. But if you have some abstract Lie group G and you get some abstract associated Lie algebra curly G, then that Lie algebra doesn't have a product. Right? I can't multiply two tangent vectors together and get another tangent vector. Okay? So if I've got some Lie algebra G, right? Often the examples we think of are matrix algebras, but just think of this as some abstract tangent space with some crazy construction using differential operators that gives us a bracket. Right? So we've got here A and B in G. There, that gives us a box AB in G. Right? No product. Right? An abstract Lie algebra, all you do, given two elements of this Lie algebra, you can box them together and get another element. There's no product. But this is a functor, right? This is a forgetful functor. Given an associative algebra, we're kind of forgetting what the multiplication is, and we just define it in the bracket. And there's some adjoint functor this way. And that means that, given a Lie algebra, I can make an associative algebra. And whenever people go on about adjoint functors at this kind of level, it's always just something that you can really come to terms with in a very concrete manner. So let me show you how to come to terms with this adjoint function in a very concrete manner. And what I've got to do is, given a Lie algebra, I've got to build an associative algebra. So here's my Lie algebra G. Okay, let's have a basis. Let's have an R basis, right? Well, yeah. Let's have an R basis x1, x2, up to xd, for d the dimension of G, right? And now here's my associative algebra. An associative algebra has got a product and it's got a 1, so it would be nice to have a 1. So let's put in a copy of the reals. And I kind of want the associative algebra to have elements. I want these to be in the associative algebra. So I'm going to put, I don't quite know I want to do this, right? x1, x2, up to xd. By these pointing, I don't want to take a polynomial ring, okay? Because polynomial rings, all the variables will commute. And these random things here, if A box B is non-zero, right? If A and B are random, but A box B is some non-zero thing, that means that AB minus BA is supposed to be non-zero. And so that definitely means that AB, so what do I mean by this? I mean this is a non-commuting polynomial algebra. Polynomial algebra. Right? So a typical element of this would be something like kind of x1, x2, x1. Take away x1 squared x2, right? That's just some random non-zero element of this associative algebra. So it's like polynomials, you can have 3 of this, take away 2 of these, and that doesn't simplify. That's the point. You can't permute the variables around. So an element of this is just a polynomial, but the monomials aren't as simple as they usually are. Okay? There's an associative algebra, and that's not the right answer, because it's much too big. Okay? Because what I kind of want is I want the associative algebra to look a little bit like the real algebra. Okay? So now we quotient this out. By relations. You see, because what I'm trying to mimic is when we have associative algebras, we can do A times B minus B times A. So let's quotient out by the relations kind of x times I, xj minus xj xi, take away xi. Oh, I've run out of space. Quotient out by the relations xi xj minus xj xi. That's supposed to be box xij, but minus box that. So let's just get this clear. We've started off with a random Lie algebra, and for me that just means a real vector space with this box, right? A real vector space with some square bracket function, and I'm trying to build a ring. Okay, the square bracket function is not a multiplication. So all I'm going to do is I'm going to choose a random basis for my Lie algebra. I'm just going to make the ring generated by that basis. So an element, I can just take random elements of my Lie algebra and randomly multiply them together. And I'm not suggesting that these are in the Lie algebra anymore. They're in some random abstract associative algebra. And I want that associative algebra to somehow give rise to the Lie algebra I started with. And so I'm simply going to throw in all the relations that look like this, right? i.e. the so let's look at the bi-ideal generated by these. Okay, this is the great thing about modern mathematics is it's quite easy to build objects that have the properties you want because we're quite good at taking a random thing, throwing in extra generators, and throwing in relations, right? We can handle non-commutative polynomial. Maybe you haven't seen them before, but you can guess the theory, right? It's kind of easy. And this is some ideal, and we look at the ideal generator, relations. We have some theory of ideals in rings, so it works. Okay. So if you do that for GL2 of the reals, then we get something generated by 4 terrifying non-commuting polynomial variables, modulo some relations which are quite difficult to understand. So what was I attempting? And when you think about it, these differential operators, I only took one derivative, right? So this is called the universally enveloping algebra of G, right? Of G. Okay, and what is an element of this universally enveloping algebra? Well, I've got all these random I've got these random things here. Remember, I can think of these as differential operators, but I only differentiated once, right? So I'm going to write these are first order differential operators. Okay? Because they're like d by dx. They were x d by dx. Okay? So an element here looks like that. So that's just a higher order. That's a higher order differential operator. Right? So for an example, if G was GL2 of the reals, and we looked at functions on the upper half plane, which is some quotient of GL2 of the reals, then we could imagine these might be things like d by dx and d by dy, and these we'd allow things like d by dx squared and d by dy squared, and so maybe the things like the quotient, things like saying that a function is harmonic, that kind of lives here because it's a second order differential operator. So we've started off with a Lie algebra, which has got a non-trivial bracket, but it was 4-dimensional. We've built some gigantic ring of differential operators, which is hugely infinite dimensional and non-commutative. We've quotiented out by some relations, and what we've got is probably still hugely infinite dimensional and non-commutative. And it's called the universally enveloping algebra of G. And so that's the adjoint functor. It's called U, right? So I've just built it explicitly. And exercise, go and check it's an adjoint functor. So what have we got? We're now in a much worse situation, right? Because we used to have 4 non-commuting differential operators, and now we've got a whole infinite dimensional vector space of higher order non-commuting differential operators. But at least it's pretty darn big. So we could look at the center. Because the center I'll tell you what the answer to that question is. The center of that universally enveloping algebra is a whole bunch of commuting differential operators, right? Answer, a whole bunch of commuting differential operators. For which we might hope that our nice functions are simultaneous eigenforms. That's morally the answer. I've given you a machine that we start off with our Lie algebra, we produce some incomprehensible object that we can't really work with, and then we take its center, which is the center of an incomprehensibly huge object that we can't really work with. And we have some hope. So now we're kind of stuck because, like, what are we going to do? So it turns out that Harish-Chandra unstuck us. Okay. Harish-Chandra found the structure. Except we have to work over C. Harish-Chandra figured out what the center of U of G was, at least over the complexes. So this is now, I did everything over the reals, but now this is just a complex Lie algebra. Right, and this is the I just change all the R's to C's. It doesn't help, right? Still everything's non-commutative. Harish-Chandra figured out what this is. So I'm going to tell you. So that's a really nice answer. And this is just, I've never read the proof, but I kind of know what it must be. I wrote some notes on it. You should read my notes, right? Read my notes. Read my notes. Because I'm going to say that the answer is it's isomorphic to something, and in my notes I write down the map. So I'll tell you what it is. So G is this random Lie algebra that's going to be maybe attached to GLN of R or whatever. And G will contain some Cartan subalgebra, which I think is often called some kind of curly form of H there, which is the torus. Right? So GLN of R, complicated n by n matrices, contains a subgroup of diagonal matrices. Right? So GLN of R, complicated Lie algebra G with some box function on it that's complicated. T, commuting linear algebra, right? Commutative Lie group. Okay? Lie algebra of T, subgroup of the Lie algebra of G, abelian Lie algebra. Right? x1 times x2, x1 and x2 have got box 0. Right? Commuting Lie algebra. Commutative group, commuting Lie algebra. These differential operators really do commute. This is like d by dx and d by dy. So complicated thing, all sorts of machinery used to deal with it. Simple thing, let's see what happens if we throw the simple thing into the complicated machinery.
So I have a question.
Yeah, go.
G equals GLN here?
Well, let's just say, why not? Because that's the only case I'm going to do, really. Or GLN of R, GLN of C. If you want, G can be an arbitrary connected reductive algebraic group over the reals. and everything I say will be true. The Harris-Chandra theorem works in that generality.
But it won't fit inside GLN, I guess is my question.
Well, you see, an arbitrary, that's the Peter-Weyl theorem or something, isn't it? I've got some, it's some algebraic thing. It's in Borel. If I've got an arbitrary algebraic group over the reals, an affine algebraic group, it will have a faithful representation. So an arbitrary affine algebraic group, I can embed it as a subgroup.
And then the Cartan will embed as...
Yeah. And then this is some Cartan subalgebra there. Yeah, so if you know the language, yeah, you go ahead and use the language. G some reductive Lie algebra. H is some Cartan subalgebra. H looks comprehensible. I've described a really complicated machine to do G, right? We tensor up to the complexes. We form some crazy non-commutative polynomial ring. We quotient out by some crazy relations, and then we take a center. We could do all that with H, but with H, the brackets are 0. So H is abelian. So when I do this with H, if I do this with H, what is this U of H? Oops, U of H. I guess it's some, it's some U of H. Let's do U of HC. It's going to be complicated polynomial rings, x1, x2, up to xd, right? D is the dimension of this abelian Lie algebra. So this is complicated polynomials in non-commuting variables, and then I need to mod out by the bi-ideal generated by, where's it gone? It's just down here. I need to mod out by the bi-ideal xi xj minus xj xi, take away nothing. So I throw in all these complicated non-commuting polynomial variables, and then I quotient out by the bi-ideal xi xj minus xj xi. So I throw in a bunch of variables, I demand that they don't commute, and then I quotient out by relations that says they do commute. And so I can do that quotient. That is the normal commutative polynomial ring. D, right? Commutative ring. It's infinite dimensional, right? D's bigger than 1. It's infinite dimensional, so it's kind of complicated, more complicated than H. H is only d-dimensional. This is infinite dimensional, but, it's finally generated, so it's kind of not that bad. It's a commutative ring. So if I throw in an abelian Lie algebra into this universal enveloping algebra, absolute nonsense, then the universal enveloping algebra is a commutative ring, and its center is, of course, just the same thing. So the center of the universal enveloping algebra of H is a polynomial ring in d variables. And we can kind of write the d variables down, right? Because they're just somehow differentiation in each of these directions. Somehow. They're all going to be they're all going to be d by dx times x, right? D by dx1 times x1 and d by dx2 times x. So this is not a mysterious thing. And I'll tell you the cool Harris-Chandra thing, right? Harris-Chandra homomorphism. I'll tell you for GLN of R. Okay. So what we do, let's let G be the Lie algebra of GLN of R. If I tell you for GLN of R, then people that know the language will just work out what it is for general G. G is GLN of R. Then the theorem is there's a canonical injection I take my Lie algebra, I tensor it up to the complexes, I take its universally enveloping algebra, which is some terrifying non-commutative polynomial ring in n-squared non-commuting variables, modulo some incomprehensible relations. And I look at the center of that universally enveloping algebra. Let's just call it Z. And it turns out that it lives in this Cartan subalgebra thing, lives in U of HC. There's a canonical map from this crazy, complicated thing that we don't possibly understand. There's just some cute little integral, and you do the integral, and it gives you, it's just basically projecting down to h, right? That's the, you average over some upper triangular matrices, and then project down to h, right? That's the proof. I'll tell you what you do, actually, more precisely. We're trying to get from functions here to functions on here. You take the functions on here, you restrict to the torus. You take the differential operators on here, you somehow restrict to the upper triangular matrices. You then do some integral that averages it down onto the torus. Then you multiply by a fudge factor, and then you say, oh, look, it didn't matter whether we took upper or lower triangular. It's the same, because we put some fudge factor that was like something involving mod a over d to the half. There's a canonical injection from this into this, and I can tell you what the image is. It's the universal HC, the Weyl group invariance, where W is the Weyl group. If you know what Weyl groups are. Let's pretend you don't. Let me do GL2. GL2 of the reals. Because GL2 of the reals is the only example that we need. It's the first non-trivial example. So let's try and figure out what's going on. So G is the Lie algebra of GL2. So the proof of this, proof is kind of like restrict to Borel, kind of integrate to average out over, average out, project down, multiply by fudge factor. Right, and now go and read my notes if you want to see the details. So G is GL2 of the R, GL2 of the reals. G, tensor of the complexes, is C times E plus C times F plus C times Z plus C times H. Okay, so this universally relevant algebra contains things like whatever, E times F plus, F times H, that sort of thing. Random, this is some. That's a third order differential operator. That's a second order differential operator. These are complicated things. But the abstract theorem says that this center of the U of G of C must be isomorphic to the Lie algebra of the torus. Well, the torus in GL2 of the reals is just 2 stars, right? So this is going to be isomorphic to the U of, I guess it's just C plus C, right? That's the Lie algebra of star 0, 0 star tensor C. So it's U of C plus C W, where W is some mysterious Weyl group. Well, this is Z mod 2Z. It's not that mysterious in this case. So this is isomorphic to a polynomial ring in 2 variables, x and y, modulo the invariance of some cyclic group action. So the Z mod 2Z action, it sends x to y and y to x. I mean, I'll tell you what it is. It's the if you know about Weyl groups, it's the normalizer of this torus. And so the normalizer of the torus contains the torus, but it also contains, in the GL2 case, it also contains 0, 1, 1, 0. You see, imagine that n is 2. I've got my torus here. That element there, if I conjugate by that element there, it sort of turns T upside down. Yeah. This is the point, 0, 1, 1, 0 times A 0, 0, B times 0, 1, 1, 0 is B 0, 0, A. And so the Weyl group is the normalizer of the torus modulo the torus, which turns out to be Z mod 2Z generated by this 0, 0, 1. So it switches things around. So now we have a problem. What are the polynomials in 2 variables which are symmetric, which stay the same if I switch x and y? Okay, and so as a fun exercise, this is C, S, and T, where S is x times y, and T is x plus y. So in particular, in the GL2 case, there are 2 mysterious differential operators. That one's got 2 letters in, so that's probably a second order one, that's probably a first order one. And if I maybe could ask that I'm an eigenvector for these differential operators, maybe I'll be nice. Okay? That's the one thing I can think of. Well, this is how it works. I tried to motivate it. Tomorrow, we'll see the definition of an automorphic representation. It's going to be great. When are we leaving again?